Okay, so thank you for being back. That wasn't for granted. At least I didn't lose anybody after lecture 1. So today I'm going to talk about a bit about the standardization path, though this course is kind of an academic nature mainly, but we are going to touch upon, what's happening with the 3GPP mainly standard, and I'm also going to talk a bit about the scenarios, so what people envisioned actually could be the use cases and applications of 5G. Is the volume all right until the last row? Can you hear me? Yeah. So just a small announcement. IIIE ICC conference, right? Many of you, I guess. So it's going to be actually held in my university in Dublin in 2020, so not that far away. So not this coming deadline, which is for 19, but if you submit papers by September, I think 2019, then most welcome to visit us in Dublin. Okay, so basically there is like a never going trend, okay, about traffic demand growing. So you do have like essentially 3 phenomena that are kind of converging these years and the last few years that gave rise to the discussion about what we should do to cope with this demand. So one comes from the traditional, let's say, dimension of cellular networks and Wi-Fi networks. That has been kind of the motivation also behind 4G, right? The other 2 arrows, so the right hand and the bottom arrow in this figure, are in my opinion newer, okay? They weren't there, I think, to the best of my knowledge in 4G, for example. So you have actually computing happening on devices more and more. Okay, they become smarter and smarter. You also have this phenomena of, for example, caching the content at the edge, cloud, right, computing and services. And then you have the things communicating. So while in the past it was pretty much a human endeavor communication, right? So of course you would have mobile phones, access points, and so on communicating, but behind them there was always a human user, right? Right now it doesn't have to be like that. Okay, so you do have things like CCTV cameras, you do have sensors of many different kinds, all the actuation systems that need to communicate in smart industry, smart cities, e-healthcare, you name it. Okay, there are many things where actually humans are not even there, except for maybe occasional checks. You have maybe somebody in the loop having a look now and then, but the system doesn't necessarily need a user operating the device, right? So all of these things combined, they actually lead to more and more traffic. Okay, I think if you just do this simple, mental experiment, remember what you were capable and actually expecting to do with your mobile phone or with a wireless device in general just 2 years ago. Let's go back 5 years, 10, 15. I think you kind of mentally see there is an exponential behavior here, right? I mean, I see for myself. I'm not honestly the most, obsessive, compulsive user of a smartphone. There are people that definitely do way more than I do. I think I'm, moderate user, and still I can see that, the usage has changed a lot, and you definitely rely more on that for business, for entertainment, just things like Google Maps, right? Or normal email, browsing, on-demand platforms. These things weren't really there 5 years ago, honestly, okay? I still remember in my PhD, so we go back a bit more than 10 years, printing out maps. I don't think I was the only one doing that, right? Now, forget about it, of course. You have Google Maps, right? So, and this increases, right, the strain on the network. I mean, it's not that they come for free, right? So there are things like to do with the frequencies, to be found. The energy efficiency is a big problem, right? I do remember with the 2G phones, you literally didn't have to charge them. Maybe every week, every other week. That's it, right? Try to do that with your smartphone and then see how long it will last. So So there are things to do, for example, with the fact that you have to make the devices more power efficient. And I think, again, we are getting spoiled by technology. As I said in the first lecture, it's like we expect now a certain level of service, and we're not going to compromise back to something worse, right? No way we would accept the download speed of 2G nowadays, yes? So what to do, definitely there is, something happening, right? And I think it would probably happen also with 6G. Again, I don't expect any plateau, any capping of this behavior, okay, as long as we can do it, because in fact more and more ideas are emerging, right, with virtual reality, with ultra reliable services, self-driving cars, and who knows what will come from artificial intelligence alone, right? Things like robotics. If you think about service robots, what they call service, it's like kind of these robots that they are sort of like waiters, assistants. They're coming, okay, they are in the market. You have things that are literally there if you want to buy them. And again, these are new things that would have to communicate, and they imply, actually, you see, what we did so far with things is mostly on the sensing side. We collect information, and pretty much that's it. We relay it to somewhere else. Same thing, by the way, with communication. Mostly, it has been a very neutral thing, neutral pipe to transfer information. All we do, modulation, coding, MAC, networking. It's always been kind of, okay, I transfer information from A to B. Now, what happens if you have not only to transfer information, but to take actual decisions, controlling a camera, for example, or an industrial robot, right? When you go to Industry 4.0, the problem is different there, because you don't have just to collect information, you have to answer back with an action. So you do have all of this dimension of control theory coming into play. Historical communication and control, they didn't really talk to each other, right? This is changing now. Other things, computation. To me, computation meant basically nothing up until 2 years ago. Nothing, okay? You kind of, again, to me the problem is transferring information. But what if it's not just transferring information, it's to to perform an operation. Very stupid example, averaging something. What changes? It's not just transferring information the problem. You have to decide where the basically addends are, right? Where you send these terms and who computes the sum. This is a new problem, right? I never saw that, and this is the most basic problem kind of you can come up with in computing. And of course you can go way beyond this. Right now there is this whole concept of in-network computation. Why? Because I mean also the application, yes, you have to compute things maybe, but it's also like new problems. For example, there are some nodes that might do more computation than others, so they run out of battery sooner than others, and that is a problem in terms of what they call network lifetime. This problem wasn't really there before, or maybe it was there but in an homogeneous way. You just have to, you just have to make sure maybe on average the mobile phone consumes less. But here you see you have maybe specific nodes. So we are kind of moving away from this homogeneous picture of telecom to something more heterogeneous. So the function you perform, you compute has a big role to play, and probably bigger in the future. Other things, storage. To me, storage was nothing really. I mean, what? USB key, I buy my hard disk, that's it, right? Now, forget about it. You have, for the last 5 to 10 years, huge amount of work on caching. So it's not just about what and where you communicate, it's what you compute, so what functions. So it's not just collecting bits, it's changing the content of variables, right? And another thing is where you store things. That's another important thing, right? Especially if you are going toward these insane latency requirements we were talking about this morning, 1 millisecond. You see, at some point you can't go faster than speed of light. So if you want to go faster than that, you have to act smartly. How? You store things in advance. So AI could help, for example, predicting the path. So if you know that a mobile phone is moving, or say a wireless device is moving toward a certain point, you already know it's going to be there. Maybe because there is a corridor, maybe because there is a street. You know historically that's where the user goes. So why do you have to wait passively? Proactively store the information, and of course the download at that point can be kind of instantaneous, right? So maybe that's the only way you can comply with this millisecond requirement. So you see, communication alone won't cut it, definitely, okay? So you need help from other disciplines, and more this is what I experience, at least in my lab, you know, in my own work, that I've been talking in the last couple of years more and more with people from AI and control. Never talked with them before, never, okay? At most, before it was a Phi guy talking to a Mac guy. That was all that as imaginative we could go. Now, way beyond that, okay? So, and that altogether means that we have to do more and better with the networks, okay? When I was giving similar courses on 4G, it wasn't that wild, definitely, okay? And now, if I just look at the pattern, what has happened since maybe 3G, 4G, I wonder what 6G will be about, maybe even wilder. I think the field is really, it's not settled in any way, and that's a good thing. So though telecom engineering is there, has been there for a while, okay, we go back to Bose, Marconi, right, and before Maxwell, so it's been there for a while, but it still surprises me how it can reinvent itself every 5 to 10 years, okay, and really very active, okay, in terms of new concepts. So this volume is there because, I mean, more things are communicating and doing things, so eventually you still have to, you know, even if you do caching or you do computing, a big part of it is still transferring information, right, and taking decisions and communicate. So even if you have, let's say, you have to decide where optimally you should store things, where optimally you should compute things, you still have to convey the information. So the communication is maybe not there for the sake of it as it used to be, but still it's a very important part of the picture because you still have to communicate information, right? Maybe for other purposes than before, but there is a lot of communication going on, maybe even more than before. Massive growth in connected devices. Definitely, again, look at yourself. I don't know you. Again, I'm not probably even the best example in terms of being very much dependent on, you know, high tech. Sounds weird because I'm professor in telecom, but I'm not, I think, such a tech geek. But there are people way, you know, beyond me, and I would say I'm kind of an average, maybe a bit lower than average, you know, user in this sense. But even if I think at my case, I probably have right now 5 to 10 devices I'm using regularly that are connected wirelessly, possibly the same with everybody in this room. If I go back again 10 years, that's already 10 times what it used to be, which was pretty much 1, yes. And again, I suspect it's going to change even more when you start to have, you know, what they call domotic, these smart houses, smart cars. There are some people that really can't wait for the new gadget, right, to come out. But other people, they just see the value in it, and I think little by little you will see how pervasive these new wireless applications will become, right? So these things are definitely going to be there for a while. I wouldn't trust numbers necessarily. I mean, I remember 10 years ago they were talking 1 trillion. Now they scale down 20 times, so take it with a pinch of salt. But definitely, 50 billion is probably not an insane estimate, right? Because you have, what, 7 something billion people, 7 devices each? Fair enough, I think, right? Definitely the use cases and requirements have been broadening up quite a bit. You do have things like car to car, device to device, machine to machine. Now, to be fair, it's not that any of all of these are super new. I think what is new is the fact that they consider all of them in the same pot, if you want. That the evolution of 4G has been kind of tasked with integrating all of these applications. Before they made, I mean, I know smart transportation has been there for a while, healthcare, right, and stuff like that, but I think it's the first time that the discourse on cellular evolution is kind of comprehensive, right? They have all of them together. And I'm going back to this, it's pretty much from the beginning, from the manifesto of 5G, they say, okay, we are about all of this. which is the first time, as far as I recall, in cellular communication history. On top of it, there is all of this green wave. Now, whether you are an ecologist or not, still you have to acknowledge you have to be sustainable about things, right? So anytime you install a new base station, you also have an energy problem. You have to feed this base station, possibly with oil or with other sources of energy. And you also have, because of the new, let's say, piece of infrastructure, you might have to drive a car there to build the thing, right? And then maintenance and so on and so forth. So every time you add to the infrastructure, it does have an impact on environment and sustainability and money. As I said this morning, there is a big business problem nowadays for operators. They can't seem to have a decent, business profitable model. It seems to me that they don't know what to do, okay? So they know they have to do something, but they're very cautious because they don't see the value because of these over-the-top guys eating up a lot of the money. So why should I deploy new base stations if I know eventually Netflix is going to benefit and Netflix is going to contribute zero to my investment? So you see, it's not completely unfair that they might be a bit conservative, but they also have their own users to satisfy, right? So I think anything that goes, along the lines of making a more profitable case, maybe sustainability and profitability go hand in hand, right? Because if you become more efficient, you save money. So these are all things that have to be more and more considered. And honestly, to my knowledge, I've been saying this even 2 years ago, I think, so nothing has changed since. I don't see a good good body of research taking into account cost. Not really. Pricing model. So either you have people that are completely isolated in the business community, they might study telecom systems, or you have like people from this side of the fence. Yeah, you have a bit of efficiency masked, like, right, maybe as a cost, but there is no serious. For example, people have been talking about ultra dense networks for how many years? I never came across a decent study on the implications of this from the fiber deployment viewpoint. They have these broadband small cells everywhere. How do you connect them to the rest of the network? Nobody knows. They just say, okay, put a base station every square meter, fine. And how does that pan out in terms of digging the trends, connecting things? And you have all the sorts of problems that come from the fixed network side, like synchronization and bandwidth. It's like you kind of say, okay, I sweep the dust under the carpet, but the dust stays there, right? So, and then somebody else has to take care. So I think this is not, for example, being taken care of very well, in my opinion. Any question, comment? Feel free to ask. Okay, so now this is super tiny, so I'm just trying to see how well your eyesight is. No, kidding. So So don't worry so much. I think you can. Hopefully you got the soft copy. You can zoom out. That's what I did, by the way, to check this. I got this from actually a PhD student of mine that is doing a PhD in collaboration with Nokia. So I'm a guy, the academic supervisor, and then he has a company supervisor, and he's doing PhD half time with us, half time with them. So he's my source of knowledge as far as standard and the industrial world is concerned. They have a very good lab, by the way, in Dublin. They're called Nokia Bell Labs now. They are kind of world leaders in things like small cells, and they also do quite a lot of good work on massive MIMO drones. So they're really, really good. There are not so many companies, in my personal experience, again, personal opinion, that are doing basic good research, probably except for Bell Labs and a few others. They're still the guys that employed Shannon. I mean, of course, they're more commercial a bit, maybe, but they're still doing kind of very good work, academic good work, actually. So it's good. It's good to see them still alive and kicking. So, by the way, so these are the releases. So the release is kind of a draft, if you want, a version of the standard which is agreed upon, and they say, okay, we are good with that. Everybody in the standard is now happy with it, and we are going about it. The standard is not about implementing the specific algorithm. It's more about giving guidelines of what you have to comply with, right? And you have to make sure the rules are kind of there. So if everybody follow this, the system is going to work pretty much, and achieving the ITU goals. Yeah, but then how you do the specific algorithm, for example, scheduling, the standard won't tell. First of all, because of competition, right? Well, probably most of all because of competition. They just want to leave it free, let the best win. But they set the rules of the game. That's what the standardization body is. So they do have, you see, like a few things that have happened over time. So right now we are actually in this part, actually even beyond this. So release 15, I think, is being finalized. That's what Professor Das was talking about, I think. And then, not again to be too picky about the single things, but you see, for example, just to mention a few things that have happened over time. So self-organizing network was there from the very beginning of the, let's say, first kind of 4G system was release 8. So then you had like things like emergency calls and integration of emergency system and cellular networks, and then you have carrier aggregation, all the story behind increasing the spectrum availability. Coordinated multipoint, so more and more like fancier and fancier MIMO schemes, also virtual MIMO, and we are going back to these schemes, by the way, in the course. Device to device, so anything with to do with near field communication, right? Machine type started to emerge, integration with Wi-Fi. 3D beamforming, so actually one thing that has happened is also that kind of using all of the degrees of freedom. So somehow we forgot the third dimension in space. So a lot of the work that has, for example, been done in beamforming has been about radiation patterns on a plane, but more and more you want actually to have uniform user experience also with respect to height. For example, for people living on, you know, skyscrapers or, you know, tall buildings, and in general, if you can actually use the third dimension, is better, okay, because you have a better view also of the tilt, right? You have the azimuth angle, but you also have the elevation angle, and you know they're trying to make full use of all of them. So especially for millimeter wave, these things are very important because you have to be very precise with the beam alignment in millimeter wave networks. We are going back to that. Okay, very high order modulations, 256 QAM. I heard about 1024, so they're pushing more and more how many bits you can put in a symbol. LTE first release, they were happy with 64. Okay, now they're pushing that too. And some things that are happening right now is like they are talking about the flexible numerology. You know what numerology is? I'm not talking about the esoteric science of numbers. I'm talking about basically the values of the parameters of a cellular system. They call it numerology. So for example, how long is the symbol period? How large is a channel in frequency? Stuff like that, okay? So they are, I mean, in the past, pretty much up until 4G, the situation was you have a kind of key application in mind, and your system is only about that. So therefore, you will optimize the values of the parameters based on what you have in mind. Why? Just because it works better, okay? You know that that's kind of your target, so why do you have to provide a lot of flexibility, which complicates things and increases cost? So for example, there is a reason why the subcarrier spacing in 4G is 15 kilohertz. There is a reason why time transmission interval in LTE is 1 millisecond. It works, and it kind of does the job for the applications we are serving. There is a bit of hint in flexibility also in 4G. For example, they have this short cyclic prefix and long, and that has to do with the fact that if you are targeting more indoor-like or outdoor-like applications, outdoor-like the delay of the channel would increase. Therefore, you need a longer cyclic prefix to cope with that. Yeah. But you see, it's probably one example. I don't think there are so many. Now the situation is with the same network, you want to serve things that are very delay intolerant, this 1 millisecond application we were talking about, or you might want to serve something that is all about pushing as much data rate as you want. You're serving things that are very static, but things that are very mobile too. They're even talking now in 5G about planes, right? Stuff like that. And So what do? You can't have a single set of values for all the parameters of the system that will do the job. So you have to kind of become more flexible, but flexibility can be exploited only if it's there in the first place. So what I mean is, if you don't design the system so that these options are available, well, how do you do that, right? If you can't change the thing, then it's useless to talk about it. So, for example, they're talking about time transmission intervals that change with respect to mobility. So if you're going very, very fast, it means the channel memory is changing, so the channel memory is shorter. The channel is changing more rapidly. So you have to actually collect information, feed it back to the transmitter, and take decision faster than before. Therefore, for this, you have two options. Either you make the provision of a shorter symbol period, or maybe you can just use the symbol period, right, like now, but instead of having a fixed number of symbols inside, like OFDM symbols, you might just pick a variable number. So if you have a faster application, maybe I use only a few. If I have, you know, a kind of slower application, I use more. Okay. Other things, for example, have to do with the subcarrier spacing, right? Because if you have an environment which is outdoor mainly, likely you will have, let me think. So, well, it depends more on the multipath really. So if you have a very multipath rich, maybe outdoor environment, you might actually, let me think. So you might have the need to have a shorter subcarrier spacing, okay? And if you have like a multipath poor environment, you might go with a broader one. So these things are happening, okay, and I don't think there is any, strictly speaking, any consensus now, except for the fact that we need this kind of flexibility. So this is kind of the story. I think I've been highlighting some of the main things, but you see, essentially every release had kind of a big thing happening, okay? So it's not that they kind of sat back and relaxed because the job was done. So you see that there are a lot of things still happening, okay? And each of these releases, you see, they're not that far apart, maybe not even 1 year sometimes, right? So there is a constant actually upgrade of the system. So that's the main message behind this slide. Okay, so just to tell you a bit where we are right now. So basically the current release, so you see, is like I said, 15 is the current one, more or less. That's true. They keep on working on the thing. So I think right now, yeah, so that's what Suvra was saying. They froze the current release, at least the current stage of release 15, I think in March 18, but they have a plan, okay, that will go on. So I think there are different waves of the 5G story, and for example, so one interesting thing here is that they talk about standalone, non-standalone. So what it means is like non-standalone, it means you will use the current infrastructure as much as possible and upgrade it as needed. For example, you might have heard about this control data plane split. So in that case, they use pretty much the macro cell infrastructure and add the relays, the small cell base stations, these kind of things. So that's non-standalone. But they are also discussing some situations where you would have a radical new deployment of only access points that rely on the new radio paradigm, so the new, let's say, technology. So I don't think it impacts us too much, honestly. I mean, just to be aware that discussion is going on. The course is kind of general, so I wouldn't worry so much as long as you're on top of things. It's okay. Now, it depends also on what you have to do with this work. So if you are a company or somebody that has to go about the real system, it's a very good idea to keep in the loop with these guys, because they are the ones that eventually decide the real system, how it looks like and what you have to comply with. If you are a researcher, what we normally do is kind of LT-like. So of course, you can't assume an access scheme that is unheard of, or you cannot assume values of parameters that make no sense. But other than that, we are good, right? But of course, the details of the control channels, of the pilots, and these kind of things are more important if you are more on the engineering side. Yeah. So that kind of draws the line for me between, say, science and engineering in this case, right? So, but of course, even if you do science in academia, you still have to do it in an informed way. So it's a good idea to keep an eye on what they do now. To be perfectly honest, I normally rely on people that are more patient than me to study standards, because I honestly get tired very quickly. The way they organize the documents is not so intuitive in my opinion. A mass of documents, not really structured. They make no effort to, to make it a bit more understandable and appealing. I understand it's kind of a collection of technical reports, but it's kind of difficult sometimes to look for information you want. So in my experience, you need somebody with that mindset and that kind of experience. I don't think you can parachute a PhD student or a professor into the 3GPP world and get much out of it. So if you need some specific information, it's way better to talk with people in the company or people that are more on this side of the fence, in my opinion. Okay, so in my case, I do rely on what Nokia does. Okay, so that's my source of information. I would suggest the same for others that are interested in this. You might get proficient in it, but I think it's very difficult if you start from scratch and you go on the 3GPP website. I don't think that's probably the way I would do it. To save time, I would first get, tutored by somebody that knows that world already, get the information filtered. Then you can get, of course, up to speed, but that's my suggestion based on what I could see in our lab at least. Okay, so what are these requirements that we talk about in 5G? So first of all, you don't have just mobile broadband, which was pretty much the story behind 4G. Was just having broadband on mobile phones, basically. Right now, we have other two main categories of applications. One is called URLLC, ultra reliable low latency communication. So this is, for example, for things like that require both very low delay and very high reliability. For example, remote surgery or smart car-to-car communication, possibly industrial applications, okay, industrial automation. Then you have massive machine type communication, MMTC. This is essentially very dense or very large in number deployment of sensors. It's like you literally blanket an area with sensors, and you have problems mainly due to the massive parallel transmission of these devices. So possibly to do access in the way we are used to is not a good idea. It's difficult to imagine a scheduler that can take meaningful decisions in short time. So they are talking about random access there, for example, more. And synchronization, forget about it. So it's funny that at some point Aloha was kind of dead because we found better system, and the world in the modern cellular systems was kind of based on scheduling, right? Now the non-scheduled, like the contention-based approach has been rediscovered because of these new applications. So you start to see a renaissance of Aloha schemes, and people really looking into that because that's possibly the way to go for this new application. Yeah, another thing that was kind of always there but never really there is satellite. Again, different community, but right now there are efforts to bring it together with the 5G story. So you do have integration between the terrestrial and satellite communication, okay? And you do have, for example, projects studying cognitive radio approaches between terrestrial and satellite. So one is the primary, one is the secondary system. So you do have these kind of things. Okay, that's about the use cases. I'm going back to that anyway. So just an information. When is your bus coming? What time? Half past 5? 5:30. Okay, good. Yeah, so I'll keep it in mind. So we'll finish latest by 15 past 5. Yeah. Okay, so the bandwidth. Well, I don't think there is any real target there. So essentially, my impression is use any bandwidth you can find. There are, of course, moves toward higher frequencies, but I don't think there is any specific requirement to use a certain bandwidth. There is I mean, if you can do refarming, good. Refarming means when you reuse some bandwidth that was allocated for another purpose. One example is digital TV. They became more efficient, so there was some spare bandwidth that was used by analog TV, and that was reused by cellular systems. Peak data rate definitely way higher than 4G. So for example, the numbers I remember for 4G were something like 1 gigabit per second in downlink and 500 megabit per second in uplink. So you check for yourself, it's like 20 times more. That's okay. We know that the rate is always increasing. Of course, spectral efficiency has to go accordingly because you have to squeeze more efficiently bits in the spectrum. And also the outage and also the average and the outage throughput have to go up by 3 times at least compared to 4G. So again, 4G and IMTA are the same thing, and 5G and IMT 2020 are the same thing. Depending on the kind of requirement, this has been proposed with different applications in mind. So, for example, when you talk about peak data rate, peak spectral efficiency, implicitly you're talking about broadband. You're talking about smartphones that move, okay? Other things, like for example, if you talk about outage, spectral efficiency, this is kind of the throughput experienced by the users in the worst position, the worst users, so to speak, in terms of conditions. Now, there is a difference here compared to 4G. So in 4G, this has always been something very much of a statistical nature. I'm happy as long as 95% of my users on average are satisfied. Period. That's what we call 5% outage, for example, or any percent. Now, if you have a requirement like ultra reliable low latency URLLC, you cannot gamble with that because you want to be assured the delay is within that bound. I'm not happy if 95 times out of 100 you give me what I want, because those 5 times maybe it's a disaster. Maybe I have an interjection. So maybe it's like, you know, I'm devising a system to control a nuclear plant, right? Are we really ready to gamble with that? Not really. Or even worse, if you are on the operation table, right, and we rely on a remote surgery, well, it doesn't help me to philosophically to know that maybe 95 other times I would have been alive if that time I'm dead, right? So unfortunately, you can't repeat that experiment. Okay, so well, maybe with another subject, right? So you see, the thing is, these kind of problems weren't really there in 4G. So as long as I push my outage to a decent value, good. But that's not what we're talking about. So this outage is kind of crucial for many applications in 5G. And it's much more, in my opinion, a lot of the story in 4G can be boiled down to maximizing the average throughput, pretty much, okay? And we have some constraint on the outage, okay? Now, in some applications in 5G, it's not about throughput. It's about making sure that whenever and whatever you send goes through, which is a very different problem. Could be 1 bit every day, right? So in that case, it's really more about maximizing the minimum throughput. And it might sound like trivial, but you are changing the whole optimization philosophy here, right? So if something that was a constraint becomes suddenly the objective function, it can change quite a lot. All of the techniques we kind of designed for 4G were based on another metric altogether. And again, you might have things that rely more on energy or cost, which was not really an issue in 4G, right? I mean, probably for the bad, because for the worse, because the mobile phones run out of batteries very quickly, right? But we never really cared. No, but if you have maybe a sensor network or stuff like that, that it's all about becoming energy efficient, again, you have to rethink how you allocate resources. Another example, if our goal is spectral efficiency or throughput, for us, it's definitely okay to maybe, you know, it's more about using as little resources as you can. If you want to be spectrally efficient, where is the spectrum at the denominator? So that guy should go as down as you can, right? Possibly 0. Well, you can't, but so that's okay. But if your goal is actually to make sure that something goes through, so it becomes more of a minimum throughput kind of thing, maybe you can use as many channels as you want. Who cares, right? That's not what you're after. So you see, before we were so parsimonious about using spectrum, let's share it, let's find it here, let's find it there, let's squeeze like, you know, 8x8 MIMO, whatever. But are we sure that's what we need? Maybe not. So if your goal is reliability, you know what? Maybe you don't need MIMO to do, you know, multiplexing. Maybe you need diversity. Maybe you need lower rate coding, okay? Maybe you just need to be sure that the spectrum is there and you get as much spectrum as you can. Maybe even spare one, who knows, right? You see that it's very different, the philosophy in optimizing these different use cases in 4G. I hope at least I conveyed that impression. So I talked a bit about these things already, but you know, latency is definitely going down for some applications very, very much so. So enhanced mobile broadband, we are talking about 4 millisecond delay as a target, URLLC 8 times less. And other things is like, let me see. I mean, ideally you wouldn't like any interruption due to mobility, so you really want a completely seamless experience of the user, okay? Reliability is part of the story, so you might want actually, so you see reliability is kind of coupled with delay in a sense. So you have to make sure you make as little mistakes as possible, but you also have to make sure the correct information is transferred within a certain time, right? So it's kind of coupled. That's why you have this URLLC. You have reliability and latency together because they are really intertwined, right? You can't have one without the others normally. Yeah? Connection density is unheard of, like million of devices per square kilometer. Here I think we are talking about you know, sensor networks, for example, possibly it's kind of even difficult to come up with an example. So 1 million per square kilometer, how many devices would it be? It's like 1,000 times 1,000, probably 1 per meter, right? Something like that. When would that be the case? Possibly, I mean, if you are monitoring something, for example, to do with the soil, maybe you need that kind of precision, right? Or you maybe want to monitor a part of the city after an earthquake. It's not that you can neglect a square meter, right? So you try. So you see, there are applications that require actually such a density, and maybe you know you can come up with others. So battery lifetime, we really want things, especially for this massive machine type communication, the sensor networks, to last kind of forever. Forever, you know, as far as we're concerned, is 10, 15 years. So you don't literally want to go there and recharge the guy any time, okay? So you deploy it there and you forget about it. It costs you more to actually go there and recharge the guy than to deploy a new guy. Okay, that's the philosophy. Or maybe it's very difficult to do. Think of the Fukushima disaster. You really don't want to go there deploying things every now and then, right? You want to do it once and for all. So you have some situations either because of economic convenience or it's actually just not a good idea, you know, from the human safety viewpoint, to go and recharge batteries. Or maybe it's just too many cheap devices. I mean, it doesn't make sense, okay? Speeds up to 500 kilometers per hour. Now, I don't know, I'm not well informed about the speed limits in India. I guess it's fair to say we're not talking about cars, not even Formula 1 cars, right? So we are talking about trains, very high speed trains, but even more so planes. I think there is now a body of work I'm aware of. They're really trying to get wireless communication, you know, on board the plane. So you do have huge problems to do with handover, of course. So they probably rely on satellite also, and coherence bandwidth, coherence time super short, right? So it's kind of very extreme as a scenario, but it's coming up, okay? And you do have big, both like flight carriers and telecom operators are looking into this kind of things, okay? So I know of guys in Ireland, they're working with helicopters, for example. So you do have all of this sort of applications, right? It can be military, but also civilian.
This is very low speed. Even the civil carrier aircraft goes by 1,000 meters.
Yes, no, I agree with you, but it's just the 4G target was 350, and it was already tough. I think 500 probably set the boundary between, you know, a lower speed plane and the high speed train. Now, I'm not a plane engineer. Suppose a plane would go what, 800, 900, right?
So there was coming the air India, they were announcing it was going by 1,000 kilometers per hour.
Yes. Well, I think first we should get 500 right. Yeah, but you're right. I mean, I think eventually, in my impression, um, there is probably a critical time. I mean, at least the engineering we did so far kind of breaks down around, I don't know, 150 to 100. I don't think we really have very reliable communication beyond that speed. So they're trying to make an effort to get it, reliable and actually of good level, also for high-speed trains. But there are moves. I know of people doing work for planes, so definitely faster speeds. I think you have to change the signal processing probably there. So they are, for example, working on new modulation techniques altogether. Okay. I think the handover has to be, of course, redesigned somehow. I suppose a better integration with satellite networks would help. I'm not working on this. I'm just speculating. I think definitely it's an interesting problem.
So, are they planning to take these devices on an aircraft? That's what we mean here?
I guess so. Yeah, I think for the trains, definitely. For the planes,
It's understandable.
yeah.
But aircraft?
Well, I know projects, okay? I'm not working directly on that, but I know people that do. I think they do have also stuff like in-flight delivery, right? So you kind of have an access point inside the plane and then it serves. It's like relaying, but then you still have to get the information, right? And it could be that for some content it's more delay tolerant, so maybe you don't have to provide a continuous communication to this relay, okay? So it's more like, I think there is also the problem of not interfering with the instrumentation, right, in plane. But there is, in my opinion, that's probably not the most challenging bit. The most challenging bit if you want a continuous operation at that speed, right? And you have integration of satellite and ground, because you can't just rely on satellite, because most probably of the content the users are interested in is at the ground level, right? So I can't speculate much further because I'm not working on this, but from physical air viewpoint, the most challenging thing is the coherence time, which becomes very, very short. And in this coherence time, you have to do everything. So you have to collect information about the network, process it, take a decision, implement it, see how it goes. And you see, so it takes a while. So I have, I think, a slide later in the course where I make a bit of calculations about the speed of light, which is a kind of severe bound. That's why I think things like proactive caching might be a good idea. So I'm just speculating now. Basically the routes of airplanes are known, right? You can't just go and wander about. So you could have, for example, relays that are already waiting for the plane. It doesn't have to be a satellite. There is this balloon project by Google, right? Why not? Having the guy there, when the plane comes, you download the stuff, right? So, and that could cut short the delay quite a lot, right? Because you don't have all of this ping pong going on. So you see some tricks we do already I think for caching at the terrestrial level, I suppose could be applied. That could be work. I'm not just informed. I guess it's a good idea to look into caching for, plane-based networks, I suppose. So yeah.
The previous point, if you could take deeper, extreme coverage, the requirement.
Yeah, so let me just check. So this basically, I think they want, essentially they want things to be, they want at least this amount of data rate, so 60 kilobit per second in uplink, literally everywhere, every time. So there is no compromise. You can't fail that. That's what they mean by extreme coverage. It's maybe not so great, but at least that you should be granted. I think I have a slide where I show visually this concept of system-wide coverage, really, not just maybe statistical, but you want an actual coverage. It's similar to what we say about delay. I think the attention in 5G is moving much more toward hard bounds. We are not, I mean, we can do statistical things quite a bit already, so we can comply with things most of the time. Now the challenge is to comply literally all the time. Okay, so that's the change in the optimization criteria, I think. Yeah.
So in the previous slide, latency in the user plane and control plane, really in terms of
Yeah. So In which
So what are the factors which influences this latency in control plane and user plane?
which slide are you?
First two lines. 27th slide.
27.
Latency.
Yes. Okay. So basically, the user plane is pretty much about the communication, right? So you are actually transferring information. Control plane is about enabling that. So for example, when you associate to a cell, going from not being selected as a user to being selected. So these things normally are longer scale. Okay. So one thing is like the current communication going on. Another thing is like the enabling of that. So I'm thinking like collection of information about the channel. So it's not just one thing. Control is few things you do, and normally you probably do need that a bit less often, and it also takes a bit more of time because it's more of a system level, I think, thing. So it's normally the requirements are a bit more relaxed just because it takes a bit more of time, and it's probably also okay to do it less often. Okay, communication happens literally every millisecond, right? So that's why you want actually the user plane to be you know more constrained in terms of delay. Now one thing has happened is like the split between control and data plane, control and user plane if you want. So basically there are some things that you just don't compromise with in terms of coverage. So the control information should be available throughout the network. You can't have gaps in the knowledge. So for example, if a base station has to advertise you know the slots to be used for communication, everybody has to know that. You can't just use a channel which is random, right? So for this they use macro cells normally. So they use cells that are at lower frequencies, again because of this discussion we had this morning, right, about the uplink and downlink, because lower frequencies are better. So macro are normally that, so they use higher power, lower frequency, and they cover pretty much the whole system. And then for data, you're allowed to use actually higher frequencies and lower powers because normally it's more targeted, okay? So it's like you know the users are there, you have to deliver information, so you are using, you are decoupling in a sense the control. You don't even need control. Control is provided by the macro, and once the small base station knows what it has to do, it just delivers the information, okay? So these things are, I think they started to be there in 4G already, okay? So you have this decoupling. Any other question?
The next slide.
Yes.
Here when we are talking about the coverage, this parameter MCL, can you explain?
Yeah, this is like called maximum coupling loss. I think it has to do with the transfer of information, you know, with the transfer of how much basically power inefficient you are when you transfer from one point to another. I'm not sure where they measure actually these two things. I think it has mainly to do with the power efficiency of the hardware, right? Yeah.
Trying to say that at this coupling loss 150
Yeah.
dB, 2
Yeah.
Mbps up downlink should be there.
I think so. So they basically say, you know, if the two things go hand in hand, because I think the more inefficient you become, the more the throughput suffers. So there is probably a threshold such that the loss is to be guaranteed. Yeah.
The WCDMA 3G technology, the 123 dB loss.
Yeah.
We
So
can expect, the
right.
coverage would be there. The voice call would be there.
So this is better, right? Because they can lose more here, I suppose. So this probably technology has evolved, I
That
guess.
is what it means, that even at the loss of
I think so.
40
Yes.
dB,
Yeah. I think that's
still have this much of a data.
that's a requirement. That's what they would like, and probably I'm not an RF hardware guy. I suppose what they mean, they did some probably back of the envelope calculation. They said, okay, to get this throughput with the current technology, we cannot lose more than this in coupling loss, I suppose. Okay, and they must have reasons. I didn't dig deeper into that. Yeah.
Because this parameter would decide that even if the signal strength is very low,
Yeah.
still coverage would be there.
Yes.
To the extent of this data rate.
Yes, pretty much. Yes. Now, honestly, even in again 4G and before, it's a bit of a magic how we provide information with such power, you know, faint power received, you know, and I sometimes my students, you know, I make an example about the Voyager probes. I mean, can you just picture how far they are? We still kind of understand what they send, right? And that is with the technology of the 70s, right? So it's kind of impressive, honestly. So I think the technology has evolved a lot. I'm not myself working on the hardware part. I think it's a very relevant part of the story, of course, especially I think if you are going into very high frequencies, terahertz, I don't think the challenge will be much of a networking nature, my personal feeling. This is much more on the circuitry side. Because of attenuation. I don't think you're really going to care so much about interference management, honestly, or MAC protocol. I think it's much more how you do it in terms of the RF part. Li-Fi is not even RF anymore, right? It's a new set of circuitry needed. So I think the higher you go in frequency, the more I think physics become nasty. So the radio engineering itself becomes more relevant than the networking part. Yeah. Yeah. Any other question? Comment? Yeah. In general, I think you have access to the slides. So if you need, even in between lectures, if you want to clarify something, just by all means feel free to email me. Okay. And yeah, keep on asking. That's great. Actually, I like it, interactive. So in a slide, I think I've just been saying that. So I'm just summing up things. About the requirements, so I don't think I'm saying anything really new. The only thing to notice is that for every single requirement, first of all, we have many of them. We have at least in this case 5, and I don't think there is anything more important than the other. They are all to be satisfied. In some situations, maybe more than one. Okay, in some situations maybe only one, but you do need to comply with all of them, and all of these are not so trivial. Okay. And now, one thing I learned in my work so far, well, we know there is no free lunch, and especially in wireless engineering. Some things you do to favor something might go against something else. For example, if I'm really about throughput, maybe I shouldn't worry so much about energy efficiency. Guess what? I can just increase my transmit power, right? So you see, that's a very silly example, just to tell you that if you want both, you can't. So you have to compromise. Maybe you have to accept a lower throughput, or you have to accept your device consumes more power, right? And now, sometimes there are some smart tricks that move the trade-off to another dimension. So what I mean, for example, when MIMO appeared, we did just that. All the trade-offs were still there, but they were in a better shape. So if you think about Pareto, we kind of moved the Pareto curve somewhere else. Right, so yes, you have trade-offs, but all of these trade-offs are better than another family of trade-offs, so to speak, right? So maybe some things like that are possible, but in general, it's intertwined, right? So you can't get one without hurting something else. So this is the figure I was talking about, the bottom one, where you see kind of clearly that they are trying to get a uniform experience everywhere. So this is like the quality of experience, no matter how you define it, say throughput. So you kind of push it up, not just about the base station locations, but everywhere. That's the idea. Okay, you would like to have even the troughs of this landscape should be not too short, right? They should be at a good level. You get some ideas about the performances. So we're talking even up to 50 gigabit per second. Again, this is theoretical. The first release of any commercial network, like I'm talking about the top left curve, it's always going to be smaller than what, of course, the final number is going to be. It can be much smaller, 10 times. Okay. Now, if you just look at the peaks, we are talking 50 times more throughput in 5G networks. That's the goal. And latency 10 times less. If I had to pick what is nastier, it's probably the latency. I think we'll get there to the 50 gigabit per second. I'm still skeptical we might comply with the 1 millisecond thing, because it's directly, you see, no matter how difficult it is to engineer a system to get higher throughput, we kind of make it. We have always done. But you can't defeat speed of light unless you come up with something smarter. So I think that's where, for example, integration of caching and communication will play a role. Artificial intelligence, prediction of patterns. If you can have an edge and anticipate things, that's maybe the way to go to cut short the delay. I think simply relying on communication is not going to work. Okay. scenarios of all sorts. Okay, so you do have things. I mean, you see, here we put like they have some wording for this. So amazingly fast and best experience follows you, which is like, for example, with you know, following users while they go by car. You might have automation where reliability is important. You might have things that focus more on redundancy than efficiency, so you just have a lot of them. You know, and if something, if some device doesn't work, some other will chip in and take over. That's, for example, this massive machine type communication is part of the story why you have so many, because you don't care about replacing them, and if some of them fail, some others will basically take over, right? Yeah, it's pretty much everything in my opinion here. So now whether we are there, that's another story. I think some things we have been doing for a while. I think what is probably new, I don't think any of this is necessarily new. I think that it's probably new the fact that we are trying to tackle all of them at with the same network. So that's kind of new. But I think these problems have been there for a while actually. So yeah, I think I already said it. The three main areas are enhanced mobile broadband, massive machine type communication, massive IoT, mission critical IoT. So the last the two bottom ones are kind of new compared to 4G. So we do have things to do with sensor networks and actuation networks also more and more, where scalability to do with large numbers is the issue, and reliability and latency for the critical one. So the left one is more about the traditional sensor network story. The right one is where actually actuation, maybe integration with automation play a role. Okay, and anyway, in terms of scalability, that's why they started to talk about this ALOA, rediscovery and random access, because of the numbers. You can't possibly optimize that. It takes too much time, too much effort. The devices are simple. You can't ask them to drain the battery to coordinate with you all the time, right? That's why, for example, we started to look into something I'm going to talk about at the end of the course, complex systems science, agent-based modeling. In general, distributed approaches, game theory, they're good because they do not rely on a genie guy optimizing, right? The problem with centralized systems is that they are bound by the intelligence and capability of the guy in charge. Yes, because it can become better than the guy in charge. The guy in charge is the guy calling the shots, right? So if you want more, the guy can do it. So the approach, if you have more nodes, is to go distributed at some point. Maybe something hybrid, maybe you need clusters with a guy in charge, but at some point you have to put a limit on the size. By the way, any organization of a human nature is like that, right? You don't have a guy in charge of a billion people, right? You have a structure, yeah, in any human endeavor, as far as I know. Okay. I don't think I'm saying so much else here. I just, you know, the purpose of these slides is to give you like kind of, you know, reminding you, hopefully, the different use cases. So you do have a lot of different things like automation, self-driving cars. Other things require actually, they are not about delay, they are not about throughput, they are just about working. So the machine type communication of the massive kind is like that. It's not about high throughput, it's not about low delay. It's probably not even about such a high reliability because you have so many, somebody will do it. It's just about somebody should do it. Okay, so it has to work for a long time, so the battery is the main concern, and you know, as long as somebody is sending this information, we are good. It's a different story with eMBB. eMBB is pretty much what we did for 4G, just probably higher throughput still and higher mobilities. UMTC, in my opinion, is kind of the new kid on the block, so it's like something I didn't hear about before 5G, at least. And this is where probably the interesting bits come into play, like this hard latency constraints and actuation together with sensing, reliabilities that imply you basically should never fail. These are things that are actually, in my opinion, newer. In fact, the first thing people did in 5G was to take care of eMBB. It was kind of a low-hanging fruit. Okay, the first part of the work has been about that. The second part of the work has been about adapting, kind of using the knowledge we have possibly from 4G to comply with machine type communication. For example, there was some work in LTE, having this narrowband IoT. So they tried to have a simpler version of LTE for this kind of sensor networks. The work on UMTC or URLLC just started. So there is a reason, because it's the newest problem. Okay, so that's still where most of the work has to be done. So you do have only some vague archive papers, initial works. You don't have really a lot of papers in this field. So if you were to suggest a topic for research within the domain of 5G, my guess would be that this is a good area. Okay, or like super fast, like what we were discussing before, network. So you have to think a bit differently than what has happened so far. So eMBB, pretty much the 4G LTE story. I mean, with the View extensions we are going to talk about. MMTC, WSN, IoT with the View extensions. But this is totally new as far as I can see. Okay, so this is where most of the work has to be done in terms of research. So if you think about the use cases in terms of data rate, number of users playing, so you can, I think this is a nice representation where where the work lies. So if you go toward higher number of users, then you go toward MMTC. If you go toward data rate, but maybe a moderate number of users, you go to eMBB. If you go toward lower data rate, but with reliability added, then it's URLLC. And then there is a region you don't want to enter, because we really don't know what to do there, and maybe even in terms of application. So what would be an application where you have literally maybe 1 million of devices per square kilometer, and they all require super gigabit per second applications? No clue. So this doesn't mean you cannot do it. Well, you can right now, but it's also maybe we don't know. We also maybe don't know what to do exactly. Okay, in terms of application.
Number of users per cell, or
This is, I think, so. I think they probably have some reference. I would say square kilometer is a good guess here, because if you look at the number, like the normal cellular communication, you would have about 100 users. So I think a cell, but a cell wouldn't mean necessarily what we mean by cell for machine type communication. It's more, I think, some area. Yeah. The equivalent of a cell surface, probably, yes.
the R and all represents what? R1, R2, R3.
Sorry?
Regions.
Yes, these are regions, yes. So so R1 is what we did in 4G, R2, 3, and 4 is what we are doing right now. R5 is future, kind of. Okay. I think I would complete these slides. It's not too much. I don't want to rush though. Tomorrow. I don't know if there is any last question before you go and catch the bus. Any comment? We don't need to rush. Okay. So I will go through some other use cases tomorrow, but I think you got the gist. And then tomorrow the idea is to finish also with this introduction, and we are going to start the second unit, okay, which is about, I'm going to go through the basics of MIMO. Before going into more complicated MIMO, I'm going to tell you something about the basics of MIMO tomorrow.
Will we be talking about VANET or MANET also?
VANET, actually, we do have some discussions about the use case, but we didn't do work. Actually, I did some work on VANET with Professor Das. It's not in this course, yeah. Not in this course, no. Sorry. Anybody else? Okay, so thank you for your attention. I think you should go and catch the bus now. Thanks. Yeah, sorry, there is an announcement.